Okay, Physics 112. I'm going to do one more video on Chapter 22. I actually got a little further in class than I guess I thought I did, so I only really need to do one more. And even this it's just me doing another example of finding the electric field produced by a continuous charge distribution, which by that I just mean that the charge has been spread out over an object. So you're not doing a bunch of point charges, but instead you've got this charge and it's spread all over this object and it's producing an electric field at different locations. And so we're trying to figure out how to figure out that electric field at some point. And in the second half of this chapter, we're doing it through integration. So this is the situation where you have a charge on a ring. So you have some sort of material that's been bent into a ring and it has some excess charge on it. And here we're trying to find the electric field. So here's our ring down here. We're trying to find the electric field at some point up away from the ring on an axis which is perpendicular to the ring, right? So this is a perpendicular axis. There we go. So we have a perpendicular axis, right? And so we're up here, and the axis goes right through the center of the ring. And we want to know what the electric field is here at this point, P. And this is basically the equation you need to have to do number 24 in the practice problems. And again, you don't have to do this derivation. You can use the equation we come up with at the end of this, which is also in the textbook, to do the problem. You don't have to do this derivation. I'm not going to make you do this type of integration. I'm just going to show it to you and make you realize that this is how these equations are coming about, and how individualistic every single point where you might try to find the electric field, every place essentially has to have its own derivation. Here we could use whatever we get from this this equation. We can use it for any point that's on this z-axis, but it basically has to be on this very specific axis. All right, and again, that's sort of what we're doing here, so it's a little hard to see. Number 24 starts over here and then goes down, but here's our picture, and you can see that this is the same situation. We have a ring, which has got a radius of capital R. We're off on some central perpendicular axis, which is called the z-axis. And we wanted to do the magnetic field at these different z locations, which once we have the equation, we can plug in those z's. All right, so if I look at this problem, I say, okay, well, I've got this this little segment ds, which is actually a length. So ds is a length. And on that little ds, there's a dq. So there's a dq on little segment ds. So this is an amount of charge, a very small charge amount on a very small length amount. And it's going to produce a dE, right? So dE is the amount of electric field that's being produced out here. I probably should have used a yellow. We'll go back and we'll do everything in pink. That would be very odd of us. So dE is essentially this. It's being produced because of that little dq that's down there. And because we're pretending like that's a little teeny point charge, we're going to use the electric field that's produced by a point charge is k dq. And then how far away is that little dq from this position P? Well, that's just this R. So R squared. And again, we're using our old equation, which is that a point charge makes an electric field which has this magnitude. K, the amount of the point charge, divided by how far away the point charge is from this position. So that's what we're doing here. But instead of a Q, we have a DQ. So instead of an E, we're producing a DE. So now I need to try and say stuff about dq. So dq itself, we're going to do like I did with the line of charge in class, where we're going to say, well, we're going to say that all of our charge, capital Q, is being spread out over this whole circle, right? So it's being spread out over this whole circle. Well, now that whole circle has a length of 2 pi r, right? That's the circumference of that circle. And dq is just the amount, this is what we call the charge density, the linear charge density, is dq times ds. So however long ds is, we multiply that by the charge length density, and we get the amount of charge which is on ds. And ds itself can be written in terms, I'm going to erase this little dq section here, but ds itself, we already have sort of certain things here. We have a z component going up away from this circle, and we have this theta, but there's a third angle here. There's an angle that goes from here to here, right? We have the circle, basically the angle of how far around in this actual circle we have. So I'm going to call this little area, this little angle, d phi. And the relationship between ds and d phi is essentially we multiply by r. So r times that little angle will give me the length, the arc length ds. So I can write that down here as well. I can say, all right, ds is r d phi. And all of a sudden, I now have an actual equation. I can say, well, dE is equal to k, and then for dq, I'll write lambda, and for ds, I'll write r d phi, and then all of this is over r squared. Now, one more thing, if I look at my relationship between r, it's a little here, I have r and z and capital R down here. So r squared is capital R squared plus z squared. Right, we have a triangle between r and capital R, z, and little r is the hypotenuse of that triangle. So I can rewrite this again and say dE is k lambda r d phi over r squared plus z squared. All right, let me re-put this down here just so we can have a little bit clearer picture. Goodness, come on, it's not gonna let me. Okay, we will go back and get it again. Where is that picture? There. So looking at this electric field that's being produced, so we're just looking at this one dE, which is off at this angle. It's off up at this direction. But if I also look at, say, from ds over on this side, that's going to produce a dE up, basically. Just on the opposite side, right, we're going to have a dE that's going up here. This will also be that same theta. And in fact, everywhere along this circle, the section, the part of this electric field that's perpendicular, that's to the z-axis, they're all going to cancel with each other. And so it's only the dEz's that remain. It's the only component that remains. The rest cancel with each other. Hopefully that's obvious. There's some symmetry as you move around this ring of charge, where only the parts that actually move up, which we can draw that as purple, only these parts, the D, E, Z's, actually remain. Well, the D, E, Z is dE times the cosine of this theta that they have drawn, right? We have this theta here. So dEz is going to be dE times the cosine of that theta. And if I look at this theta a little bit more, here's theta. The cosine of theta will be the adjacent side, which is this Z, over the hypotenuse, which is the R. So I can take my equation up here for dE. I'm going to make this a little smaller now. But I can write that dEz is my equation for dE, which is this, k lambda r. But now I'm going to put in a z d phi. And then remember that little r is going to be the square root of r squared plus z squared. So now I had a little r squared before. Now I have little r to the third power. And so I end up with r squared plus z squared to the 3/2 power. Now this is just the dE, so to actually get Ez, I need to do this integration, k lambda r z d phi over r squared plus z squared to the 3/2 power. Now, z is a variable. Everything else in there is a constant, k, lambda, r. But z is a variable, but it doesn't depend upon phi. It's just how far up the axis are you. So in this integration, z is a constant with respect to the d phi. So everything comes out. And then the limits of this integration. So phi, again, remember, is this angle down here. It's how far around are we. So we're going to go all the way around. We're going to go all the way around the circle from 0 to 2 pi. In other words, we want to go all the way, from here, we want to go all the way around in phi. So everything comes out. I end up with k lambda r z over r squared plus z squared to the 3/2 d phi from 0 to 2 pi. Well, that's very simple. It's just phi. It's just 2 pi. So again, k lambda 2 pi r z over r squared plus z squared to the 3/2 power, 3/2 power. 2 pi r times lambda is actually equal to q. It's the amount of charge in the first place. And so the book has actually made that simplification. And we have k q z over r squared plus z squared to the 3/2. And this is our equation for the electric field. It's all in the z direction. And for looking at number 24, it says, what's the magnitude of electric field when z equals 0? And z equals 0, right? When z equals 0, then the electric field is equal to 0. Z is 0 on the top. There's not a 0 on the bottom, and so E is equal to 0. When z is equal to infinity, then our electric field has got, it's got k, q, and it's got an infinity in the top, but it has r squared plus infinity squared to the 3/2. This is essentially infinity over infinity cubed. Well, infinity cubed is a bigger infinity than infinity is, so this is 0. And so the electric field is also 0 when you get out to really high distances, which also makes sense. The further you get from this thing, the more, the less the electric field should be. For part C, in number 24, it says, in terms of R, at what positive value of Z is that magnitude a maximum? So in order to determine the maximum, you need to take the derivative of the electric field, right? Let's make one more page here. So add a page. For part C, you're going to need to take the derivative of the electric field with respect to Z and set that equal to 0 to get your max, right? When you have this as a function of that, then we can sit there and we can figure out where we get the maximum value. Because what we're seeing is that when Z is equal to 0, in other words, when you're down here, let's erase some of this stuff. When you're down at this thing, at the bottom, the electric field is equal to 0. And when you're out at Z is equal to, when you're out at Z is equal to infinity, the electric field is also equal to 0. So there must be some place in between these two places where you'd have some maximum. And so you just wanted to determine what that is by taking the derivative of electric field with respect to Z. That, in other words, using this equation, take that derivative, set it equal to 0, and solve for Z. And that will tell you the location where you have a maximum. We don't really have a minimum here. Electric field doesn't have a minimum value. This is really the magnitude of the electric field. All right, and then I think part D just asks you to plug in if R is actually equal to a certain number and Q is a certain number, what's the maximum magnitude? So you put into your equation from part C, you put in these R and Q values, which are given, and get a number. I will point out that I did put on our OAKS page earlier today my solutions, or scanned version of my solutions for the practice problem. So you can look at my answer to number 24. I'm not going to do the derivation for the equation you can use for number 34, which is right here. So number 34 says you have a disk of radius 2.5 centimeters. That's your capital R. So in number 34, it tells you that R is 2.5 centimeters. It's a charged disk. It tells you the surface charge density. So this surface charge density is this sigma in this equation. And it's essentially the Q that's on that over the area now, because the charges is being spread out over a line, over a linear sort of thing, like 2 pi r or some length. It's over some area. And so it has units of charge per area, right? We have per meter squared here on that upper face. What's the magnitude of the electric field produced, again, along some z distance away from this? And this derivation actually uses the result of the previous derivation, and it is also in the textbook. But you don't have to do the derivation. You can just use this equation. All right, so that's how I'm going to leave chapter 22. We'll do more finding electric fields, but using different techniques in chapter 23.